Okay, we have just a little bit of time. You might have noticed I'm limping a little bit. I broke my foot on the Sunday before spring break. Luckily, it's just the fifth metatarsal, and it's a clean break and it's healing well, but I have to go in and hobble around a little bit for the time period. But the other thing I wanted to talk about was, oh, I don't need this, I want preview, is this. This is the Hays County COVID-19 dashboard. Okay, and the cool thing is the positivity rate in Hays County is only 2.35%. And I said I would stop wearing a mask when I lecture when it dropped below 5. So if you don't mind, I'm going to lecture without my mask on, but still stay 6 feet away from it. Okay, so this is really good for us. And I don't know if you've seen this or not right here, but there's only been 3 new cases in the last 7 days, only 160 actual ones, but they also have it by city. So you can actually do just San Marcos. There are only 23 known active cases in San Marcos. Although 181 people died, but you know that's just San Marcos too. That's not good. But it's getting better. It's getting better. That's all I can say there. But anyway, I wanted to show that kind of new demographic thing. So let's get back on to chemistry. We're our 2 o'clock class. We're in chapter 6. And we just finished substrate effects. No, we were on this one right here. Yeah. Okay. So we were just talking about, let me double check. Oh yeah, that one right there. Okay. So we were talking about how the SN1, SN2 reactions are really, really versatile. Okay. We can make a whole bunch of different functional groups by choosing our nucleophile. Okay. And so in all these cases, we choose a nucleophile that gives us the functional group we want to know. So make sure that you understand what functional groups get produced by each of the nucleophiles, and then that way you can get into knowing exactly how to synthesize the new material you want. Okay, so now we're going to switch gears a little bit, and that was SN1 and SN2. So those are substitution reactions, right? So we start with sp3 hybridized carbons, and we end with sp3 hybridized carbons. So we all have sigma bonds. The next thing we're going to talk about is an elimination reaction. We're going to break 2 sigma bonds and make a pi bond. Okay, so we're actually going to eliminate 2 things. Okay, so in the case here, we are going to have something is going to leave. And in this case, it's these 2 atoms here are going to leave. And the way they're going to leave is in a specific order in which that these electrons are going to end up coming down here to form our double bond, and these electrons are going to leave with the leaving group. Okay, so we can have it do it in a couple different mechanisms. So when we're looking at this, the first way we're going to look at this is we're going to use base. So we're going to remove an acid. So we're going to move a hydrogen and a chlorine, fluorine, bromine, or iodine. So it's going to be removing an acid. When we remove an acid, we call that dehydrohalogenation. Hydros meaning hydrogen halogenation right there, and D meaning remove. So we're removing an equivalent of acid. And when we do this, we create that double bond. Okay. But we have to define some of these things because that double bond shows up at a specific location. Okay. So what we're going to have to do is we're going to have to start telling this right here, the carbon with the halogen on it, right here, is what we're going to call our alpha carbon. Okay, it has the leaving group. When we did substitution reactions, the reactions happened at the alpha carbon. Okay, but in beta, we have to remove a hydrogen from an adjacent carbon. So we're identifying those as beta. So these are beta carbons right here. And the double bond is going to form between the alpha carbon and the beta carbon. Okay, which means we have to remove the hydrogen from the beta carbon. And we call these beta hydrogens because they're on a beta carbon. Okay, so that way, when we lose this to base and when we lose this as a leaving group, we end up creating a new bond between our beta and our alpha, giving us our new alkene. We have our conjugate acid of whatever base we had, and we have our leaving group, leaving as preferably a weak base. Okay, so questions on that? So we have alpha carbon is the one with the leaving group on it. In this case, it's chlorine or bromine or iodine. And then we'll get to one where we actually can lose a water as well. All right, so there has to be a couple different ways we can do these reactions. And there are, just like we had two different mechanisms in our substitution reaction, we can do an E2, and like an SN2, it's bimolecular. The base and the substrate are in the transition state at the same time, okay? So that's our E2. So that's analogous to our SN2. But then we also have an E1, which is unimolecular. And just like in the SN1, the unimolecular E1 forms a carbocation. So you're going to form a carbocation. And so you have all the problems of forming a carbocation associated with that, okay? So the difference is literally, the idea here is that if your nucleophile has any base strength at all, it can come and do the substitution reaction on the alpha carbon, or it can act as a base on a hydrogen on a beta carbon. And so the competing between those is what we're going to see, okay? So in the E1, we have to wait for it to form the carbocation. In E2, we have our base driving up. So that means we have very similar processes happening in our different mechanisms. So let's talk about dehydrohalogenation. So the first thing we have to do is identify our alpha carbon. Yes?
So E1 is where it's like competing. So is that like the rate determining step?
The carbocation is the rate determining step.
Okay.
So that's why E1 and SN1 compete, because once you form that carbocation, the base can pull a proton off to give you E1 product, or the nucleophile can attack the carbocation.
Okay.
So it can do either, and that's why they're always competition.
Okay. And that takes a long.
The breaking the bond to form the carbocation takes the longest time. Everything else is fast. Okay? And we're going to have a chart that can compare and contrast those by the end of this lecture. So keep that in mind. All right. So what we have here is we have a tertiary alkyl halide. And so that makes, since the halide is on the bromine, that's going to make this carbon our alpha carbon. Okay. So that means we're going to form a double bond between that carbon and any other carbon that has a hydrogen on it. Okay. It must have a hydrogen on it. So in this case here, we have 3 equivalent methyl groups. Okay, so we can take it off any of these. Okay, but we're going to learn some rules for how you're going to where you're going to put the double bond. And we're going to learn 3 rules for that, and we're going to do that today. So in this case here, we're going to take a base. So this could act as a nucleophile, but it's also a very strong base. So what we're going to do is we're going to have the base come in, start pulling on this hydrogen. These electrons are going to kick in. These electrons are going to kick out our bromide ion, okay? And in this case, we only form one product because it doesn't matter which hydrogen it picks, it'll all give the equivalent product. Each of those methyl groups is identical and we'll get the same product, okay? So when we have an option though, we could get 2 different products. Now, if you notice here, we have this beta carbon right here has 1, 2, 3 beta hydrogens on it, okay? And our alpha carbon is over here because it's the one with the halogen on it. And that means that this is a different beta carbon because it only has 1, 2 hydrogens on it. So we have a choice, right? We have the one with 3 hydrogens on it or the one with 2 hydrogens on it. Okay, so if we use this is a big bulky base. Remember, this is T-butoxide. This only does eliminations. It doesn't do substitution reactions. So we're going to see that used a lot. What can happen is we can form the first product is between this first beta carbon and the alpha, and that gives us a terminal alkene, an alkene at the end of the chain. okay? But if we, in contrast, did it between the other beta carbon, we would actually end up with a different product. We would actually end up with an alkene between the alpha and beta, and we'd have an internal alkene. That's where the alkene has attachments to both sides. Okay, so and they can both form, but there will be 3 rules to show you which one is favored. Okay, so let's look at the mechanism real quick. So in this, because it's bimolecular, we have to have our base come in. Let's go with this. We have to have our base come in and using its electrons to make a new bond with hydrogen. Okay, then the electrons that were bonding the hydrogen to the carbon have to come in here and form our pi bond. And then the electrons that were holding this, because you can't have 5 bonds to carbon, kicks out a bromide ion. Okay, so it's just like in an SN2 reaction, it's a concerted reaction. Happens all at once. So you form that transition state, and then all of those bonds make and break at the same time. So we're making a bond here, we're breaking a bond here, we're making a bond here, and we're breaking a bond here. Making 2, breaking 2. Okay, so, and only one of them is on our substrate. That's the one we want to talk about, and we make a pi bond. Okay, so that means our rate law depends not only on the concentration of the base, but the concentration of the substrate. Okay, so that means our energy diagram is going to look much like the SN2 energy diagram. We're going to have our base come in and start to pull on this hydrogen. Now notice, look at our transition state here, okay? Look at all those dotted lines. Those are the things that are this one's being formed, this one's being formed, and then this one's being broken, and this one's being broken, all at the same time, okay? So it makes sense that we would want the electrons to kick in and then the leaving group to kick out to give us our final product. Notice one of the bonds that's formed is something that's not on our substrate. That's where the hydrogen is. So we don't care about that, but we actually ended up forming our new double bond here. And so we only have the one activation energy, and then it cascades down to products. Okay. So I said there's 2 possible reactions. The other one is analogous to the E1, the SN1, and the fact that we form that carbocation. So that means we only have the dependence upon the alkyl halide, just like in an SN1, okay? So it's unimolecular, we have a first order rate law, and we form a carbocation, okay? So in the case of this, we have a slightly different mechanism. We have our slow step, breaking this bond right here, breaking that carbon-bromine bond, okay? So that means if we have a tertiary alkyl halide, it can break that bond and form a nice stable carbocation. And then if we have a very weak base that's not very nucleophilic, instead of having it attack the cation here, it'll actually pull a proton away and let those electrons come in and form our double bond, okay? So we still end up forming that same double bond. It's just we do it through that carbocation first. When that carbocation forms, that makes the alpha, the beta hydrogens more acidic. So they can be pulled off with weaker and weaker bases. Now you're thinking, oh, well, wait, hold it. How are we forming the double bond with the electrons next to that carbocation? Well, let's look at, remember when we had our carbocation, that it was hyper conjugated, stabilized by having that bond between the hydrogen and the carbon. So there was this overlap already in here. So that makes this hydrogen easier to remove. And then these electrons just kick in and form the double bond. So when your base removes the hydrogen, these electrons stay here and form our new pi bond, okay? So that hydrogen becomes more acidic once we make that carbocation, okay? So that means our energy diagram is gonna have 2 humps, okay? With our slow step being our hard to break bond here, giving us our highest activation energy here. And then this is our carbocation here. And then we have a smaller activation energy where it comes in and pulls this proton off, giving us our product. What's the other interesting thing about this energy diagram? The reaction is endothermic, okay? We're taking away 2 sigma bonds and making 1 pi bond. A lot of these reactions are endothermic. There's more energy in the product than there was in the starting material. Okay, and we're gonna see that in chapter 7. Okay, so I'm confused. I have 4 different things that can happen and they all use the same thing. Well, no, we actually have a thought process that'll help us decide whether we're going to have an SN1, SN2, E1, and E2. The first thing we look at is nucleophilic strength. Does it have a negative charge on it? And is it typically not is it not a base? Is it just a nucleophile? If it's just a nucleophile, we're probably going to do your SN1 or SN2, right? Because it's not a base. Then we have to look at size, okay? And the reason we look at size is things like T-butoxide can't act as nucleophiles. They are a non-nucleophilic base, which means they can only act as base. So whenever you see it, you're gonna go, oh, base, elimination, I need to work on that. So that narrows down your choices. Temperature. Turns out that substitution reactions, because they are kinetic, are ruled by their, the speed of the reaction. But when we talked about acids and bases, those are thermodynamic, right? They have equilibrium, which means that kinetic reactions work faster if they're held at lower temperatures. They're more likely to do a substitution reaction. If you take that same thing, like let's say ethoxide, run the reaction at 10 degrees, you're going to get mostly substitution because substitution is kinetic, okay? But if you run that same reaction with alkoxide at 80 degrees, now it's going to do elimination. Elimination is preferred at higher temperatures because it's now acting thermodynamically, acting as a base. Okay, yes?
Is there like a specific number where for temperatures, it switches from that substitution?
Generally, if you look at it and it doesn't have a temperature, that's room temperature. And that would be considered a lower temperature. If it's any temperature 50 and above, that's considered a higher temperature. Okay, so I mean, there's an intermediate there where you might get a little bit of both, but the more you heat it up, the more it's going to go elimination. The more you run it at that lower temperature, the more substitution. Okay, good question. And the last thing is our substrate. Okay, as we know, tertiaries can't do SN2, right? Because there's no room for the nucleophile. But it can do SN1 and E1 because it can form a carbocation. Tertiaries form great carbocations. But it can also do an E2, okay? Because we're not worried about the alpha carbon anymore. We just see how sterically hindered the beta carbon is. And the beta carbon's 1 over, so it might not be hard to get a base in there to pull that off. So that's why tertiaries can do SN1 and E1 in competition usually, and because the carbocation, but they also do E2, okay? Now, if you have a weak nucleophile or base, water, methanol, acetic acid, then all it's going to do is wait to form the carbocation. So in strong bases, you have E2. In weak nucleophiles and bases, water, methanol, ethanol, acetic acid, you have to wait for the carbocation. And those are polar protic solvents which support carbocations. So it'll support the SN1 and E1 reaction. Now, in your secondaries, it actually can do them all, okay? If you have a good nucleophile, you're going to get substitution. If your nucleophile has any base in it, you're going to get a mix of substitution and elimination, SN2 and E2. Okay. If you have a sterically hindered base, the T-butoxide, you can only do E2 because you don't have, it's not nucleophilic enough. But if you have a weak base, you still can form a secondary carbocation. It's just going to be very slow. And when you form that secondary carbocation, it's going to compete between SN1 and E1. Yes.
Is there ever a case where we would have to like do the reaction and we'll see the reaction of a mix of SN2 and E2? Or is that?
You wouldn't necessarily, well, you can. If you ran it cold and then ran it hot, you'd get two different products.
Okay.
But what we're going to do after this is we're going to look at drawing the products of both the E1 reaction and the SN1 reaction, because they're always in competition. Okay. So, but you can have, you're going to see a lot of examples, especially with the tertiaries and the secondaries, where it's pretty obvious based on the strength of the base or the strength of the nucleophile. Okay. Now, the primary alkyl halides don't form carbocations, so you don't have to worry about E2, E1, or SN. All you have to worry about is SN2 and E2. Now, E2 will only happen if you have a hindered base, okay? Because it's not as stable as if it was a secondary or a tertiary. So you have to have a strong base, okay? But if you have a good nucleophile, you're gonna do the substitution reaction. But if you have a sterically hindered base, you're always gonna get E2. All right, questions on that? Don't worry, we have a table. So, all right, so here's our table. Okay, I've put this on Canvas empty, and I'm going to talk you through this table, and I want you to go ahead and get the empty one and talk yourself through the table and fill in this and then double check it, see what you have here. Okay, so let's talk about this. Primary methyl alkyl halide, the first thing here is a methyl, okay? If we have a poor nucleophile, nothing happens, okay? It can't form a carbocation, it doesn't want to do anything, so it can't do anything. But if you have a good nucleophile that's not very basic, it's going to do substitution. Okay. Now, if you have a good base that's not hindered, it's going to do substitution. Why? Why can't it do elimination? There's no beta carbon. It's just the methyl group. There's no beta carbon. No beta carbon means no beta hydrogen, no elimination products possible, okay? So that means even when we go with the strong hindered base, the only thing it can do is SN2. It's really slow, but the only thing it can do is SN2. Do we see why that one only has SN2 with good nucleophiles, but not with poor nucleophiles, because it's a primary. Now, if we have an unhindered method, if we have an unhindered primary, again, the poor nucleophiles in those polar protic solvents make us want to do carbocations. Primaries don't make carbocations, so no reaction. Okay, but in a good nucleophile, we're going to get SN2 all day. In fact, it's going to be great. It's going to be fast. And even in a small base, you're going to get SN2 because it's unhindered. It's easy to get it in there and act as a nucleophile. However, if you heat it up, you can get the elimination. Now, if you go to the hindered base, it can't act as a nucleophile anymore. Zero substitution, and we get our E2. Okay, so do we see how, look at those four things, you know, the type of substrate you have, the type of nucleophile you have. Is it basic? Is it sterically hindered? Now let's talk sterically hindered. If your primary has some big groups nearby, even though it's still a primary, we're going to get no reaction for poor nucleophile. We're going to get SN2 for a good nucleophile. But if you have a primary that is crowded, your base cannot do substitution on a crowded alpha carbon and will therefore act as a base on a beta carbon, pulling a beta hydrogen off. And then, of course, with the hindered base, it's E2. Secondary, you can finally form a carbocation. So you get slow SN1, SN1. Mixture of both, always. Okay. But a secondary does SN2 quite well with a good nucleophile. However, if it's not a good nucleophile, it's a base, it then eliminates. Because our alpha carbon is getting more crowded, it's a secondary there, and therefore we want the reaction, our base is going to go attack our beta carbon and give us that E2. And again, the hindered base gives us E2. And then on tertiary, we have SN1E1, and because that's got to form that carbocation. Even in a good nucleophile, we get SN1E1 because sterics, we can't do the sterics. And because of sterics, we get E2 and E2. Only attacking that beta carbon and that beta hydrogen. Okay, questions? So by looking at what we have, what kind of nucleophile we have, and then we can eliminate most of our choices just by looking at the type of nucleophile, the type of base, and the type of substrate. Okay, so go ahead and download this and kind of work through it a couple times till you get it convince yourself why each of these boxes makes sense, and then you should have it down. Okay. All right, so that's the end of chapter 6, and we're going to kind of continue on to chapter 7 because they're really closely related. Okay. No questions. So chapter 7, and let's go ahead and take roll. So for spring break, after I broke my foot, my wife and I went down to South Padre Island to celebrate our 31st wedding anniversary. So they were very short walks on the beach. They were very painful, but we were, you know, one of those cute old couples who hold hands and stuff. So it was really fun. Left my teenagers at home for them to fend for themselves, and we just had just the two of us. It was quite good. And we left before the craziness started on Friday. So we were good. All right, everybody got their stuff done. All right, so let's go back up to our chapter. This is our next chapter. The homework has been moved to Friday because I hadn't got to the lecture, so the homework's moved to Friday. But we will be having a quiz up to cyclohexanes, which we'll get to today. Okay, so let me talk about, when we talked about alkenes in chapter 2, we said there were two types. We had a cis version and a trans version. And I said it'll get more complicated when we get up to our next chapter. In this chapter, we are showing if you have more than 2 substituents on an alkene, you have to call it something else. Okay, so in the case of that, if you only have 2 substituents, you can use cis and trans. But the rest of the time, we have to use what we call the E and Z method. So in the E and Z method, what you do is you find the 2 carbons that your double bond is on. You assign priority on the first carbon, you assign priority on the second carbon, okay? And so in this case here, these methyl groups are highest priority compared with the hydrogen. And now we look along the axis of the double bond and we say, oh, both of these groups are on the same side, okay? That's what made us cis, right? Okay, well, in this nomenclature, that's gonna be Z, zusammen, meaning together, okay? And you can remember it because Z groups are on Z same side with Z, okay? So they're on the same side. And likewise, trans is, we had, this is the higher priority, this is the higher priority. We draw a line down the middle. They're opposite sides of that double bond, and therefore we have what we call E, which is entgegen, which means opposite. So we have our E and our Z, and so they are analogous, but now we can do it with more than 2 groups, okay? So let's look at this one. We're gonna do this one right here. We have 1 carbon, we have 2 carbons, so this is our higher priority one. And we just have to circle it. We don't have to like assign it 1, 2, 3, 4, like we did with chirality. And this here. Notice we are going to use the exact same rules we used for chirality to assign priority. Atomic number, go out until there's a difference, double and triple bonds, and isotopes. Use those same 4 rules to assign priority here, but we only have to go to 1. Okay, so then we go to this side here and we assign the priority. Oxygen is better than hydrogen. We look at our line right here. They're on the same side, so it's Z. Okay, and again, over here, they're on opposite sides, and therefore that's our E. Okay, so do we understand that? Okay, so it's just a slight change from what we have. And like all of our chiral names, that goes at the beginning of the word. So if we're naming this, the E and the Z are going to go right up front. Okay, where the R and the S would be. Okay, so let's go ahead and look at these. There's an error on this slide, by the way, so you know. Okay, so on this one right here, we're looking in here on this carbon here. This is our higher priority. Then if we look at this carbon right here, this is our higher priority. So we're going to draw our line down the middle and see they're on opposite sides. So that makes it what? E or Z? E. Right. Okay. So let's look at this one here. So we have on this side of the molecule, we have chlorine versus carbon. So that makes this our number 1 priority. We have carbon versus hydrogen. So this is our number 1 priority. Draw our line. They're on the opposite sides of that line. So they are E. Okay. So this is getting pretty simple, right? Okay. So let's use a few more rules here. We have a carbon with a carbon and a chlorine on it, but then we have a carbon with a chlorine on it. So that makes the chlorine is our first different one. So that makes this our first priority. We have a carbon with 2 carbons on it, but a carbon with an oxygen. The oxygen wins out. So that makes it on the same on that side. So if we draw our line, they're both on the same side. Therefore, we have a Z. Okay, so let's do this last one here. We have a carbon with a carbon and a carbon and a hydrogen. So this is our number 1 priority here. And wait a minute, chlorine is higher priority than oxygen because it's higher in number. So that means that this is actually on this side. And if we draw a line here, it means they're on opposite sides of the line, which gives them E. Okay, does that make sense? Now you can actually go back and do the chiral thing on the back sheet, and that'll help you with the E and Z as well. And then they'll double check. Okay. All right, we did that. Okay, so now let's talk about alkenes and stability. I said that in that elimination, we have a possibility of having one alpha beta carbon or a different beta carbon, but which do you choose? Okay, it's going to come down to stability is what it's going to come down to. So a terminal alkene is an alkene that has at the end of a chain. So it typically only has 1 substituent on it, and it's at the end of the chain. If it has 2 substituents or more, we call it an internal alkene. Okay, and as it turns out that internal alkenes are more stable than terminal alkenes. And I'll get to why in a minute, but I wanted to say that those are more stable. The other thing that we want to look at right away is that the E is more stable than the Z. Why? Okay, so let's look at their, so in the E, they're just like both facing out in 2 different directions, right? Now, what if you're in the Z position, you have your methyl groups, they're starting to butt up against each other and they're sterically hindered and they're going to pull. That's going to strain that bond. That's going to make it less stable. So we have this interface between the 2 groups that are attaching there, making it less stable. They're pushing out against each other and therefore they're less stable. So now just racking and stacking, internal alkenes are more stable than terminal alkenes, and that trans alkenes are more stable than cis alkenes. Okay, So how do we know this? Do we just kind of make numbers up and, yes, but people do, but not this. We actually have a way to measure this. And the way we measure this is we measure the heat of hydrogenation. Okay, so what we do is we take the thing, we take our alkene and we hydrogenate it and we see how much heat is given off. Okay, the more heat given off, the more energy it had stored. So the less stable it was. If it only gave off a little bit of heat, it was already pretty close to its stable form, right? So the less heat it gives off, the more stable it is. Okay, so let's look at that. Okay, so if we just took our terminal alkene right here, this is butene, and we hydrogenated it, it takes 120, it'll give off 127 kilojoules per mole of heat. Okay, so, okay, we don't know that number is, could be big, could be small, we don't know. So let's compare it to a cis alkene with the internal double bond. We said before that the internals are more stable. Let's see if that's true. Well, when we hydrogenate that, it gives off only 120 kilojoules per mole. So that means there's a 7 kilojoule per mole increased stability in the cis. Okay, well, we said that trans were more stable than cis. So what's that? So we go and measure that. And that is 115 kilojoules per mole. So that's significantly less. That's 5 more than that. So a total of 12 kilojoules per mole more stable than the terminal alkene. Okay. So now we can use this actual number of giving off heat from this reaction to give us something about the stability of these different alkenes. Okay. Okay. So one thing to think about here is that the double bond is sp2 hybridized. The sp2 hybridized means it has 33% S character, and the S is the small one on the inside. It holds things more tightly, right? So if it holds electrons more tightly because it's smaller, those sp2 hybridized carbons are willing to accept electrons. Okay. Now, the sp3 hybridized carbons, the ones around it that are tetrahedral, are only 25% S character. So they are willing to have more P character, and they can donate electron density. Okay, less that character lets them donate that. So what that means is that the double bond wants more electrons, and it can pull electrons in from the groups, just like in carbocation stability. So the more groups we have donating, the more stable the double bond is, because it's pulling in from every carbon you add, it's going to pull in a little bit more electron density. So what that means is that an unsubstituted alkene here, this is just ethylene here with no substitution at all, those hydrogens cannot donate any electron density. That's already an S orbital. So we have our highest release of heat, and this is in kilocalories per mole, so it's a different unit. But just by adding one group here, it drops it by almost 3 kilocalories per mole. Okay, just one group. So that carbon is stabilizing that double bond by that. Now, if we look at our cis and our trans is lower than our cis right here. Okay, and that's because we want to, these are starting to butt up against each other. But then look at this. We can have 2 substitutions, but it's not helping very much. Okay, they're both on the same carbon, which means there's no donation on this side. There's only donation on this side. So it actually makes it less stable than the trans alkene, closer to that of the cis. Even though there's 2 carbons there, it's only donating to one of the carbons because the hydrogens can't donate. And then by adding a third one, it should drop again. Yeah, it's less than having a second one. And our last one is the most stable of all. So by adding more and more carbons around your double bond, it gets more and more stable. Okay, so if our more substituted double bond is more stable, which products do you think are going to form? The more substituted ones or the less substituted ones? the more substituted, and it's because they're more stable. Okay, so let's go ahead and look back at this dehydrohalogenation reaction. We're also going to learn a dehydration reaction, but that's not going to happen until Thursday. Don't forget the quiz on Thursday, and the quiz has to be taken between 11 a.m. and 3:20 p.m. If you take it online, it has to be taken between those hours because of some anomalies. I'll let it go at that. Okay, so of course we have the one we've already talked about is the dehydrohalogenation. So let's look at that one and how it affects with our E2 reaction. So in this, we have a concerted reaction. It happens all at once. Okay, so we've drawn this such that our beta hydrogen is opposite our leaving group here, because these electrons are kicking in and these electrons are kicking out. Okay, just like in our substitution reactions, when it was happening concerted, we're making a bond and breaking a bond at the same time. So they have to be 180 degrees apart, right? We're going to look for that same thing to happen. Okay, E2 is always better than E1 because of side products. E1 will always have a little bit of SN1 in there as well. So we always prefer the E2. And notice on the table we just looked at, most of the reactions were E2 reactions, unless we were using water or methanol or acetic acid, which are poor nucleophiles. Okay. So we can use, you can use a bulky base to use sterics to get some stuff moving along. If you're using a non-nucleophilic base, that also will prevent SN2 reactions. So T-butoxide always does the E2. The other bases, if they're hot, they'll do elimination. If they're cold, they'll do substitution. Okay, and therefore higher temperatures will favor elimination. Right here. Okay, so being that we have alpha and beta carbons, and we know that we want to make a more stable alkene, a more substituted alkene, that means that our reaction is regioselective. It's going to pull off a specific beta proton to give the more stable product as the major product. So it's a regio-specific reaction. So let's look at that and try to see how we can, oops, not that one. Not that one. There we go. Okay, so in this one, we have a tertiary alkyl halide. So this is our alpha carbon right here. And we have two types of beta carbons. We have the beta carbons that are just the methyl groups here. And then we have the beta carbon that has two hydrogens on it. And it has the methyl group here. Okay, so if we were going to look at that and we were going to say, let's start with the, let's start with the beta carbons on these methyl groups. Since they're all equivalent, we're going to make the transition state that is going to account for having our base come in and remove a beta hydrogen on one of these methyl groups. So we have this bond here forming in our transition state, this bond forming in our transition state. We have this bond breaking in our transition state and this bond breaking in our transition state. Okay. So when we do this right here, we are going to have it go into this transition state where our carbon here is going to have the slightly more positive charge, maybe. Okay. So that's a transition state. But let's instead use the beta hydrogen over here. In this transition state, we have this bond breaking and this bond breaking. And notice that this would give a more substituted carbon right here. This bond's making and then this bond's making. Okay. So the transition state that gives the more substituted alkene is actually more stable by a little bit. Okay. So if we did that and we went to products, we would end up with the first transition state giving us this product. And notice this is a disubstituted alkene, but it's also a terminal alkene, right? It's got two hydrogens. Okay, but the alternative one is, look, this is tri-substituted right here. internal alkene. So it's tri-substitute. It's the more stable. Therefore, it's going to give us the more the product. Do you get some of the other product? Yeah, a little bit. You will usually get a mixture, but the more stable product will be the major product. Okay, so let's look at that transition state. There's not a big difference in energy between those two transition states, but it goes toward what is the nature of this carbon. The more substituted the carbon is, the more stable that transition state is going to be. And notice that we have, there's not a big difference between them. So the one on the bottom here, does it go faster or slower than the one on top? Faster, because it has a lower activation energy. Okay, so that means it goes faster because it has a lower activation energy. There's not much difference between the other transition state, but it's going to go slower because its activation energy is high. So you should get a majority of one over the other. And it's always going to be the more substituted product is going to be the faster formed, and it's going to be the major product. Okay, so let's look at substrates. Okay, so we saw on our table there that E2 happens on all of our substrates except for the methyl alkyl halide if we had a strong bulky base. But primaries will do substitution if you have a strong base, but everybody else does E2. Secondaries and tertiaries do E2, and hindered primaries will do E2. So E2 is going to be pretty popular here. And as it turns out, the E2 reaction increases having alkyl halide, having a tertiary alkyl halide. It's the opposite of SN2. Why is it SN2 so slow for tertiaries? Sterics, right? We're trying to substitute on a carbon that has three other things on it, plus our leaving group. Okay, well, in E2, we're not worried about that carbon. We're on the beta carbon. We're on a hydrogen on the beta carbon. We're one carbon over. So the idea that we can actually use a bimolecular reaction and start pulling that proton off one carbon over makes a lot of sense. And so we can see it maybe easily removing the hydrogen and the leaving group at the same time. So these are competing but opposite in reactions. So the more sterics you have, the more E2 you're going to have. Okay, on your substrate. Okay, so let's look at this. By increasing the number of R groups, we end up with a more stable product. Now, let's look at the difference between primary and secondary. Okay, if we have our primary right here, we only have one choice for a beta carbon and one choice for a beta hydrogen. It's going to be that one or that one. That's all we get. Okay, and because that's forming this transition state, it's going to give us a less stable product because it gives us the mono there. So our primaries go slower because they can only give us terminal alkenes, and therefore they give us a slower product. But notice it also only gives one product because you only have one beta carbon. Okay. Okay. In the case of a tertiary, especially in this one right here, we have 3 equivalent methyl groups right here. It can choose any of those 9 beta hydrogens to form. And because we're not worried about how blocked this group is, these methyl groups are really easy to get to. So our bulky base can go just pluck one of those hydrogens off right there. But it's going to pluck one that'll give us the most substitution. And in this case, it'll only give us a di substitution. And it's the most stable one we can have. And it gives us that one product. Okay, so those were pretty easy. Let's try to figure out some rules for predicting where the double bond's going to end up. Okay, so in the case of that, we actually have our first rule. Our first rule is called Zetas Rule. Okay, Zetas Rule says that you will form the more stable or more substituted, which is the same thing, alkene, when using normal bases and normal substrates. Okay, what I mean by normal is, primary, secondary, tertiary, and your alkoxides and your T-butoxides. Right? So what we can do is look at this and say, okay, on this example here, we have beta hydrogens here And those are the same as those because they're both secondary beta hydrogens. And we also have these beta hydrogens, and those are primary beta hydrogens. Okay. So which beta hydrogen is going to be preferred to pull off, a primary beta hydrogen or a secondary beta hydrogen? The secondary beta hydrogen, because that's going to give you the more substituted product. So the product it'll give us is this alkene right here, but there'll be a little bit of that beta hydrogen, that other one, that'll give us the minor product. And notice the minor product is disubstituted, but this one's trisubstituted, making it more stable. Okay, so we call this rule Zetas Rule. Okay, so what we'll see here is that our relative rates also follow that tertiaries faster because it's going to give us the more substituted, and we have choices for our beta hydrogens. The secondaries are going to go a little bit faster than the primaries, and the primaries go the slowest because it only can give us terminals. Okay, so this is our first rule. Make the most stable alkene you can. Okay. Now, there's two other rules that combat with Zetas Rule. The only two things you have to worry about are, number one, if there's already a double bond in the substrate, you're going to form the double bond that can be conjugated with the substrate. Remember what conjugation is. Conjugation is where you have a double bond, single bond, double bond. Okay, and conjugation is good because these are pi bonds, right? And you can have the p orbitals overlap with each other in conjugation. So if you can put two double bonds together, you will. So in the case here, we already have our pi bond here, and our chlorine is on this. So this is our alpha carbon here. Okay, that gives us two choices. That's the beta carbon here or the beta carbon here. Now, if we chose the beta carbon over here, that would give us a tri-substituted alkene. Okay, that would be the right answer, except we have a double bond. Now, if we make the one on this side here, now we'll have our double bond here, and all of these pi orbitals will be conjugated. That's why it'll break the rule. So conjugation breaks Zetas Rule. So we call this the conjugation rule. Okay. So our major product is going to be the conjugated diene, and our minor product is going to be our isolate. Notice it's major and minor because, you know, those activation energies aren't too big, but they're big enough to give us a major and minor product. Okay, so the same thing happens with benzene, but why? Well, benzene is 6p orbitals in a ring that are perfectly conjugated. So it's going to want to put the double bond in conjugation with those so they can be shared. So you'll see it, benzene ring, single bond, and then the double bond. Like in this product here as our major product, even though it's only a disubstituted alkene, it's still more stable because of conjugation. And this is the more substituted, the trisubstituted. However, we've broken conjugation because we don't have p orbitals on these two atoms, on this atom. We do have one on this atom. Okay, so we cannot use Zetas Rule when you have double bonds or rings or benzene rings. Okay, so you use the conjugation rule. All right, now we have one last rule, and it's called the Hoffman Rule. The Hoffman Rule is if your substrate is such that it has a choice, it has differences between methyl groups and other alkyl groups, and you have a super big bulky base like T-butoxide, you're actually going to change your product ratio. So in the case of the small base here, okay, we have a tertiary substrate, we have a small base, and look, I gave you additional information. What's the additional information I gave you? 70 degrees C, that makes it hot. So we know we're going to try that elimination reaction. And we're going to see that these beta hydrogens are more favored than these under Zetas Rule because it gives them more substituted alkene. So that means this is our major product, and it's 69%. But we have 6 of these and only 2 of these. So some of these are going to end up coming off. And we're going to get the less substituted, only 2 substitutions on here. But it's a slower reaction because it's less stable transition state, and therefore it's less. However, let's change one thing. Let's go from that small base to this big bulky base. Okay, now this beta carbon here is harder to get to than these beta carbons. And therefore, these beta carbons become favored with this big bulky base. So when you see T-butoxide, we knew that it was a big bulky base and it doesn't act as a nucleophile, but it's also going to give us a flip-flop of our products. We're actually going to get the less substituted as our major and our more substituted as our minor, only because the T-butoxide can't reach the hydrogen over here. Okay, does that make sense? So those are the 3 rules about regioselectivity. You have Hoffman's rule is if you use T-butoxide, you're going to get the less substituted, the one with the methyl groups. It's going to attack the methyl groups. You have Zetas rule, which means you're going to get the more substituted if you have a regular base. And you're going to get conjugation if there's already a double bond in your system. Okay, so that should help you select your products and your major product from all of those. Okay, so now let's talk another part of stereoselectivity on the system. And we're going to have to use, let's see, not Fisher diagrams, but Newman projections to show us how this works, okay? So in the case of our stereoselective reaction, we want to say, okay, we're going to form a double bond here in the middle. And if we take one of these hydrogens, we get one of these products. And if we take the other hydrogen, we get a different product. Okay, well, in here we know that the transalkene is the more stable product. And it turns out it's also the major product when it's made. Okay, and we have the cisalkene right here is our minor product. So it must be the slower reaction or the less stable transition state. Okay, so that means that we can have one product if our base comes up at the top and rips off that proton, one product if it comes to the other. But why? That doesn't make any sense. Well, remember, our E2 reaction is a concerted reaction. It has to form, break, and make bonds all at the same time. That means your orientation with your hydrogen and your leaving group should be anti, just like in our SN2, where they have to be 180 degrees apart. So what does that look like? Okay, so what that looks like is we want our hydrogen and our leaving group to be what we call antiperiplanar. Okay, they're basically in the same plane and they're anti to each other so that the bonds can make and break all at the same time and not crowd into each other. Okay, now you can actually do the reaction when it's like this, but it's not as easy to do the reaction. There's too many things coming here. So you can do the reaction, but this is by far the more sterically, energetically preferred conformation. Because it's the more sterically, or the more energetically preferred conformation, that's going to be most likely to be our transition state. Okay, so how does that affect our reactions? Okay, well, if we look at that anti-elimination right here, we want to see where our big bulky groups are. Okay, so in the case of, let me see, do I have it on the next slide? Yeah. So in the case of these benzene rings, we're going to draw a Newman projection of, we're going to start on, we're going to do it down from this direction here. And let's do our Newman projection. So I'm going to do a hydrogen, and a phenyl ring right here. And we're going to do the back one. And let's put the phenyl ring opposite it there. And let's put a bromine down here and a hydrogen right here. Okay. So in this case here, our hydrogen and our leaving group are antiperiplanar to each other, which means when this kicks in and forms the double bond, the two benzene rings are on opposite sides of the double bond as it forms, right? Do you see why they're opposite sides of the double bond? Okay, so that's going to form this product here. Okay, so let's draw it and take away the other one. And the way we do that is we have to get this hydrogen right here has to be up in this position here. So we have to rotate the front around. So let's redraw. Let's leave the back where it was. And we're going to draw a hydrogen around a benzene ring, and then our leaving group, bromine, here. But we needed that other hydrogen there. So that means this phenyl group is going to be over here now. This hydrogen is going to be over here, and this hydrogen is going to be up here. All right, so this hydrogen is now antiperiplanar with that. So we had to form this gauche formation to get the other hydrogen antiperiplanar. How stable is the gauche versus the anti? It's less stable, right? It's less, so it's going to happen less. Therefore, it's going to be less of a product. So we have a stereoselective reaction, but we have to look at it from the perspective of your projection, your Newman projection. Okay, so let's try a couple more of those right here. And so if we have our position here, let's draw our CH. We have a CH3 on this side, a phenyl ring on this side. Then let's draw our circle here. We have a methyl group up here. We have an H over here and a Br. Okay, so in this configuration, if we removed this, the only hydrogen we can remove on this side, then we would have to have it in this configuration to do our forming our double bond. Yes, question. Yeah, gauche is where the groups are 60 degrees apart. So in this, these are gauche, and the methyl group and the phenyl group are anti, and the hydrogen and the bromine are anti. Okay, so we only have these two methyl groups in the gauche position. We have the big group over here, so that when we form this double bond, that means the two methyl groups are going to be on the same side. CH3, CH3, and the phenyl group is going to be on the side with the hydrogen. Do we see why? Because when we form that double bond here, these are on this side, these are going to be on the other side. And that gives us our final product there. But if we had the other isomer, and this is actually another isomer, we would have C, we would have H, and then the methyl group is on this side here, and the phenyl group is on this side here. And then to get that periplanar, we're going to want our bromine down here. Our hydrogen is sticking out on this side, and our methyl group is now sticking out on this side. So this other isomer has it, to get this to be periplanar, that hydrogen and that bromine to be periplanar, we're going to end up with the methyl group and the phenyl group on the same side, and a methyl group on the hydrogen side. And so if we look at our final product, we see the phenyl and the methyl are on the same side, the methyl and the hydrogen. So it's best when looking at this to figure out which isomer, which E and Z isomer you're going to have, to try to draw that Newman projection. And then just remember, you're taking this and putting the double bond right here. So whatever's on that side stays on that side, and whatever's on this side stays on that side. So this means that if we have two options, the more stable one is going to be the major one. And so that usually gives us our trans isomer. Okay. So, and we can look at that a different way here. In the case of this, we only have one hydrogen option. We have two hydrogen options here. In this particular configuration, the two largest groups are anti to each other. And so when this forms our double bond here, we're going to form it so that it gives us our trans alkene. Okay. But if we look at this one here, we can have this configuration here. We still have a hydrogen that's antiperiplanar from the bromine here. And so when we form the double bond here, we're going to form the cis isomer. Okay. Now, Why do you only form, why is one major and one not major? Well, the anti-configuration here is more stable than the gauche configuration, making this our major product. They'll still both form because of the rotation, but it'll be our major product. All right, questions? All right, let's keep going. All right, so let's do a couple examples here. So we're looking at a secondary alkyl halide, and we have a good base. It's a small base, so we don't have to worry about it forcing it with the Hoffman rule, so we can use Zetas rule, okay? So we have choices. We have this beta hydrogen here, and we have this beta hydrogen here. I'll learn to stop tapping. Beta hydrogen here. So which is it going to do, the one on the left or the one on the right? The one on the left is going to give us a di-substituted alkene. The one on the right is going to give us a terminal alkene. So you're going to want to do the one on the left. So when we do that, what we end up with as our major product is the internal alkene right here. And it's a mixture of cis and trans with more trans. Okay, so this reaction actually gives us 3 isomers. We get mostly trans, some cis, and some of the terminal alkene. Okay, because of cis is more stable. I'm sorry, trans is more stable, so we get more of that. The internal is more stable, so we get more of that. And then our last one is the mono-substituted, which is our least stable. Okay, but what can happen is, if we look at this group here, all right, so this is going to give us our most stable alkene, right? So we want to do it on that side, right? We cannot make an alkene with that carbon. Why? We don't have any beta hydrogens. There's methyl groups. We don't have a beta hydrogen. We're not making a carbocation. So we can't use that carbon to make that structure. So that means we have to make it with this one or that one. Okay. And from that, this is our more substituted one. And this is our least substituted one. So what we're going to see is we're going to have our major product is our internal group here. And then with the methyl group away from the T-butyl group. Okay. And again, to prove it to yourself why, you want to draw your Newman projection and see where the methyl group is and where the T-butyl group is. In the case of this, the hydrogen is on the side with the T-butyl group and the 2 methyl groups are gauche. In this minor product, these 2 are gauche and these 2 are gauche. So that's more sterically hindered. Therefore, it's going to not form that bond. Okay, so Zetas rule is correct here, but you have to use a Newman projection to get the right major and minor product, because they're both equally substituted. They're all both substituted by 3, but we have a major product because of that Newman projection. All right, so the last thing I'm going to cover today is cyclohexanes, okay? So let's look at cyclohexanes and let's think about that antiperiplanar. So we have to have our leaving group antiperiplanar to a hydrogen, okay? So let's look at this one right here. So we have this one here and there's a hydrogen here also, okay? And so we have this hydrogen here and this hydrogen is gouged to that chlorine. This hydrogen's gouged to that chlorine. This hydrogen is gouged to that chlorine and this hydrogen's gouged to that chlorine, which means this carbon right here and this carbon right here are the ones that are anti to that chlorine. Can this eliminate in this form of chair? No, it doesn't have a hydrogen in the antiperiplanar position, so it cannot eliminate in this position. But what's the good thing about cyclohexanes? When you flip them, all your axials become equatorials and all your equatorials become axials. So if it goes to chair 2, we now have this other formation, and you have your hydrogen is axial, your chlorine is axial, and these are anti to each other. So in cyclohexanes, you want to have the chair conformation that has your leading group in the axial position and a hydrogen in an axial position. That tells you where it will eliminate. Okay, so that means either one of these can go. So that means we're going to form a double bond somewhere in there and give us a single product. Okay, so what's really happening here is, in this case here, with the chlorine in its equatorial position, it does not react in an E2 reaction. So it just sits there and then it waits until it flips over to its axial. Now that it's in the axial position, it can do the elimination and gives us product here. Okay. So is this a fast reaction or a slow reaction? It would be slow, right? Because it spends more of its time in this than in this. So you have 10% of your time, it's in the position it'll actually react. So 90% of the time, it can't react. 10% of the time, it can react. And then when it can react, it does. So you have to wait for that second chair formation to get it to form. Okay. All right. So that means that once you have different positions on here, different groups on here, you can actually make a reaction that happens and forms specific products. Okay. So in this case here, we have a methyl group and a T-butyl group in their equatorial positions. That's their most stable position, right? We're lucky because the chlorine is also in its axial position, which means we can eliminate it. Okay. So we have an axial one here and we have an axial one there. Okay. So because this is going, so that means that we can eliminate in this direction here or in that direction there. Which direction do you think it's going to eliminate? If we go to this side here, we'll only have a di-substituted alkene. But we have a hydrogen over here. If we go to this side, we'll have a tri-substituted alkene. So it's going to go to that side to give us our tri-substituted alkene, which is over here. But what if we had a different isomer right here? If we had the different isomer, so the chlorine was also in its equatorial position, and the methyl groups and the T-butyl groups are all in equatorial position. This one can't react. This one can't react because there's no axial hydrogen. We have to wait for it to flip over here to its more stable form. But look what happens when it forms that more stable form. The axial hydrogen is over here. There's no axial hydrogen here, and there's no axial hydrogen here. So it has to use that, giving us our less substituted ring, our less substituted alkene. It's going to give us a di-substituted alkene. Okay, so lining that hydrogen and that chlorine up to get them an antiperiplanar tells you which your product is going to be. Okay? And I think I have one more. Yeah. So whenever you're looking for this, you always want to have your leaving group on your axial position, and then you look for the axial hydrogens. If you don't have, you only have one axial hydrogen, it's going to go to that, form that one product. Okay. So let's see. Okay. No more than one beta carbon from the hydrogen can be removed. Yeah, you can't get axial hydrogens from the third carbon away. Okay. Let's see. All right, so I'm going to stop there. And so the quiz on Wednesday will be up to cyclohexanes. Practice those Newman diagrams to show you which is your major product. Is it going to be cis or trans? Is it going to be E and Z? Practice E and Z. Yes.
So it's chapter 6 and 7.
Chapter 6 and 7, focusing, on E1, E2, SN1, SN2 comparisons, and then all the elimination and the alkene stuff. Okay, everybody at home get that too? All right, I'm gonna go ahead and stop sharing. And we will head on out.